Good day, and welcome to an episode of my reviewer series for civil engineering topics focusing on fluid mechanics problems. For this episode, a wooden storage vat full of oil with a specific gravity of 0.8 in the shape of a frustum of a cone 2 meters diameter at the top, 4 meters diameter at the bottom, and 3 meters high. The vat is provided with two steel hoops, one at the top and one at the bottom. Given that, we are to determine the following: the hydrostatic force on the side of the vat, the distance of the hydrostatic force from the bottom of the vat, and the force in the bottom hoop. Starting with our first unknown, ang hinahanap natin na force is on the side of the vat. Therefore, ang effect ng force na ino-observe natin is acting in the horizontal direction. Furthermore, yung usual na ginagawa natin in order to determine an unknown force is by static equilibrium. And maa-apply natin to by doing methods of section since closed nga yung figure natin. And yung exerted force naman is coming from the fluid inside our container. For this specific case na merong axial symmetry yung figure natin, ang gagawin nating hati is just exactly at the middle. So, talagang mayu-utilize natin yung mga given na dimensions. And with the separated section as the system of our force equilibrium, we can already start performing our solution. To make it more convenient, let's showcase the figure muna with the cross-section as our main view. Recalling the formula for hydrostatic force, unit weight of the fluid times the height of the centroid from the top surface times the area perpendicular to the applied force. Solving for this, isa-isahin natin yung mga present variables. For the first one, hindi given ang unit weight ng oil, but given tayo ng specific gravity. And as you all know, the specific gravity of a given substance is equal to its unit weight over the unit weight of water. Using this, we can transform the equation to determine the value of our unit weight just by multiplying both sides with the unit weight of water, which, as we all have encountered before, has a value of 9.81 kilonewtons per cubic meter. Plugging these values into our equation to solve for the unit weight, we will get an answer of 7.848 kilonewtons per cubic meter. For our next variable naman, para makuha yung h-bar distance, need muna natin hanapin yung centroid. Medyo mahaba yung solution na need natin gawin para makuha yun. Kasi for one, di siya like yung standard shapes natin na may maikling equation para makuha yung location ng centroid. Kasi diba, yung square, half lang ng height. Tapos pag triangle naman, 2/3 ng height mula sa top. Dito sa trapezoid figure, kailangan hati-hatiin pa muna yung area into basic shapes. So kung titingnan natin, yung area mabilis na lang natin makukuha. Tapos, pwede rin naman na i-perform agad yung sa pagkuha ng h-bar. But if we are to consider the other unknowns, such as yung sa question number 2, we may want to look at a different approach. Kasi when it comes to determining the exact location of the application of hydrostatic force, need mo na isolve yung tinatawag na eccentricity or yung distance na mula sa centroid ng area natin. And in order to do that, meron tayong involved na moment of inertia in which pwede lang natin siya masolve considering the basic shapes separately. So, panibagong mahabang solution na naman. Instead of solving this na sa bawat question i-rewrite natin yung pag-separate ng shapes, ang gagawin natin is sa simula pa lang, hati-hatiin na agad natin para all throughout sa pag-solve natin ng situation, yun na yung gagamitin nating division ng area. And looking at the figure, there are actually two ways kung paano natin pwede gawin yung paghati. For the first one, hahatiin natin yung area into two triangles, where yung isa, nasa taas yung base, tas yung isa naman nasa baba. And as we all know, ang area ng triangle is just 1/2 of base times height. So, apply lang natin siya on both triangles. And getting the centroid for the following triangles naman, gawin nating reference line yung top height ng figure natin. For triangle 1, yung distance ng centroid niya from the reference is 1/3 of the height, giving us a value of 1 meters. And as for triangle 2 naman, ang distance ng centroid niya from the reference is 2/3 naman ng height, giving us a value of 2 meters. Now na alam na natin yung unit weight, centroidal heights, and individual areas nila, plug lang natin siya sa hydrostatic force equations natin, then sum up lang natin yung values nila. With that, we will get a total value of 117.72 kilonewtons. This time, let's try another way to solve this problem naman. Bale, ang division ng area naman natin is by separating the rectangle in the middle. Then we'll have 3 divisions. And actually, pwede natin to simplify into 2 divisions if we consider the 2 triangles as 1 area lang. Kasi kung papansinin nyo, pag pinagdikit natin yung dalawa, makakabuo ka pa rin naman ng basic shape. So, madali pa rin natin makukuha yung centroidal height niya. And at the same time, mas mabilis na yung pag-jot down natin ng solution. Pero it's up to you guys pa rin naman if mas prefer nyo yung 3 hati. Kasi applicable pa rin naman yun. Pwede nyo itry after nyo panoorin tong video para makapag-practice din kayo. Moving on, similar to our first solution, kunin muna natin yung mga areas nila. So for the first area, ginawa dito is kinuha muna yung area ng individual triangles, tapos nag-multiply by 2 na lang since pinagsama na nga natin yung dalawang area nila. Tapos rectangle area naman natin is just base times height. After that, we just get the centroid once again, referencing from the topmost height. So para sa triangle 1 and 2, consider na natin siya as a whole. Tapos, kunin lang natin yung 2/3 ng distance, which is 2 meters. For our rectangle area naman, half lang siya ng height, so we'll get a value of 1.5 meters. Since kumpleto na ulit yung variables natin for hydrostatic force equation, apply na natin to for each division, then sum up lang natin sila. And once again, we'll get the value of 117.72 kilonewtons. So this just prove guys na sa kahit paanong division ang gawin sa hydrostatic area, determinable pa rin yung force by adding up the individual determined force from each area na dinivide natin. This time, let's move to question number 2. Then as we proceed, ang gamitin na natin all throughout is yung section ng area na ginawa natin sa second solution. Pero I highly suggest guys na after this video, try nyo pa rin i-continue yung ginawa nating first method para malay nyo, mas madali or mas gamay nyo pa pala yun. Pero anyways, alam na natin kung ano yung magnitude ng forces sa bawat area and also yung total force. Ang hinahanap naman this time is yung distance ng total force mula sa bottom ng container. In order to do that, the determinable distance that we can solve for this situation is by using the eccentricity equation, which we have mentioned na rin kanina. Pero recalling what we have discussed earlier, mahihirapan tayo solve to considering the whole area kasi nga, need natin mag-solve ng moment of inertia. And recalling our equations for moment of inertia, similar lang siya sa pagdetermine ng centroid, wherein may standard basic shape formulas tayo na mas madali masundan. So following that approach, ang magiging thought process natin is kunin muna natin yung mga eccentricity ng bawat sectioned area, tapos referencing from the bottom of the figure, minus natin yung mga eccentricity sa bawat centroidal height nila para makuha yung distance ng forces from the bottom. Then para makuha yung distance ng total force mismo from the bottom, multiply lang natin siya sa variable distance niya, then equate to the sum of the individual forces ng mga hinati nating shapes times yung distances nila mula sa bottom. So technically speaking, we just use the idea of Rignon's theorem wherein yung total force times distance or yung total moment natin is equal to the sum of the moments solved from our divided areas. To start our solution for number 2, in order to have a value for these following distances, solve muna natin yung eccentricities ng individual forces natin. Rewriting our formula for eccentricity, ang unknown variable na lang natin dito is the letter I, or yung tinatawag nga natin moment of inertia. And in order to solve for that, kailangan familiar tayo sa mga formulas na nadaanan na ng karamihan sa atin nung inaaral pa natin yung mga physics concepts. Pero before that, let me just show something on making our eccentricity formula more simplified muna. Although yung ibang variables natin except I is already determined and listed in our table, gusto ko lang ipakita tong ibang form ng equation para just in case pwede nyo rin siya i-apply sa pag-solve nyo ng ibang problems. What I'm actually talking about is, since alam na natin yung value ng force F equal to gamma h bar A, pwede natin to ipalit sa eccentricity equation natin para ma-cancel out yung gamma variable. So looking at this expression, we just actually verified na no matter what type of fluid yung gamitin natin, mapapalabas pa rin natin yung same eccentricity value as long as the same shape siya. I think this is something talaga na need nyo malaman para maging convenient para sa inyo ang pag-perform ng solutions. Pero going back, sige gamitin na natin tong formula na to. Solving for the moment of inertia ng triangles 1 and 2 combined, gamitin lang natin yung formula na base times height cubed over 36 and we'll get a measure of 1.5 meters raised to 4. Now that we have that, salpak na natin siya sa eccentricity formula natin. So I is equal to 1.5. For our theta value, that is just the angle of the direction of force with the horizontal. So since horizontal na mismo yung force natin, 0 degree angle lang siya. Then yung h bar A is written in our table values na. So with this, we would get an eccentricity of 0.25 meters. For our rectangle area naman, same process lang. Naiba lang sa moment of inertia kasi yung gagamitin natin na equation for that is base times height cubed over 12. That would lead us naman to an eccentricity value of 0.5 meters. So now that we have our distance values, pwede na natin siya i-apply sa Varignon equation natin. Let's denote our unknown distance as letter D. Therefore, our total force of 117.72 kilonewtons times distance D is equal to the sum of force 47.088 times yung distance niya mula sa baba, which is centroidal height of 1, minus eccentricity of 0.25 plus 70.632 kilonewtons times its distance, which is centroidal height of 1.5 naman, minus eccentricity of 0.5. Take note nga pala, yung centroidal height natin dito and yung h-bar value is magkaiba. Kasi yung reference ng h-bar is mula sa taas, tas yung ginamit naman natin is mula sa baba. Baka malito lang kayo dito, so be mindful talaga. Given the following equation, shift solve lang natin to sa calculator or perform lang kayo ng multiply on both sides, whichever is more convenient para sa inyo, and we'll get a distance value of 0.9 meters from the bottom of the vat. Now, for the last question, consider na natin pati yung still hopes as part ng system ng static equilibrium natin. Actually, dito sa figure, meron ding tension na na-experience yung mga top hoop natin. Pero sa gagawin nating approach, di na masyado need yung involvement nila. Kasi ang gagawin natin, we would take a moment about the top surface, thus canceling the top hoop tension values. So using moment equation, yung total force ng 117.72 multiplied by the distance from the top, which is total height lang minus yung nakuha nating value ng distance niya from the bottom, and equate natin yun to twice the tension force at the bottom as shown in the figure, multiplied by its distance from the top. So since ang unknown natin is T, shift sum lang natin to sa calculator, and we'll get a value of 41.202 kilonewton tension force. Finally, natapos din tong isang medyo mahabang discussion ng problem. If there are any further questions, feel free to ask in the comments below lang. With that, this situation is finally solved.